So, let us start with a new topic here in multi-rate signal processing itself, which is digital filter banks. A digital filter bank is a collection of filters with a common input and a common output. So, the idea is very simple here. We have a discrete time signal and we are filtering it through a bank of filters, and that is why it is called a filter bank, because it is a bank of filters. So, this is H naught of z, this is H 1 of z dot 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 till H m minus 1 of z, and let us designate these signals as x naught of n, this is x 1 of n, so on till x m minus 1 of n. And these bank of filters, they are called the analysis bank. Why are they called analysis bank of filters? Because you are taking the signal x of n and you are analyzing this signal x of n through these filters, right. This could be perhaps H naught could be basically your low pass filter, H m minus 1 could be your high pass filter, and all of these other filters could be possibly be band pass versions, right. So, this is basically analysis bank, and these signals x naught of n, x 1 of n, so on till x m minus 1 of n, they are called sub band signals. It is very important. They are called sub band signals, and the name is pretty intuitive and obvious. They are called sub band because you are filtering them in different frequency bands, and this is why they are called sub band filters. So, like the way we have this analysis bank, one can think of synthesis bank, so which is again pretty straightforward. So, we have signals y naught of n, y 1 of n, so on, and they are passed through some set of filters. These are basically synthesis filters, and our hope is we can reconstruct x back, right. I mean, you can think about this as basically your sub band signals, and these sub band filters are filtered through a bank of synthesis filters, which is termed as synthesis bank, and then you basically sum the output of all the signals coming out of the synthesis filters, and hopefully you get your reconstructed signal. Right. This is a very crude form. There are a lot of details which we will explore during our journey through this module. So, a question that naturally comes to us is, what could be the nature of frequency responses for Hi of z? Right. This is a question that you would probably ask to yourself. So, H naught could basically be the low pass version, H1 could be some band pass version, H2 can be probably a next version of this filter, basically with some frequency translation. As you can see, this is basically overlapping. There is a spectral overlap. An alternative way to think about these filters would be to treat them as non-overlapping. And you may wonder, what is the connection to having overlapping frequency responses versus non-overlapping frequency responses, right. So, if you were to think about having filters that have non-overlapping responses, it is beneficial for us because there is really no aliasing that you are introducing. So, therefore, when you are trying to reconstruct these things by passing them through these filters, they do not overlap in the spectral domain. So, therefore, you will get a clean signal. But if you think about the caveat of this structure, you will have to really design filters that have very steep responses, because you really have to notch and null them off at certain points in the frequency spectrum, right. And this is a critical parameter, because if you have to have such sharp frequency responses or the transitions, then your filter order just goes up. I mean, if you just look at the formula from Belanger, I mean, this is the empirical formula. I mean, this is inversely, filter order is inversely related to the normalized transition bandwidth, right. If the response is to be very steep, then your order really jacks up. So, this is one thing. So, it is easy to visualize conceptually having filters that are non-overlapping in their frequency responses. It helps us overcome aliasing and all these things, but we have a problem because our orders can be quite high. But if I have aliasing, I mean, if I bring in this overlapping nature of frequency responses, then okay, my filter order is less, etc. I am able to tolerate, because I can have a more steeper skirt in this transition band. I mean in the transition bandwidth I can basically have a more gradual slope, right. It is basically less stringent in terms of my steepness, right. So, however, that would cause aliasing and I have to overcome this aliasing error through some means in the process of doing this this filtering through a bank of analysis filters followed by synthesis filters. I mean I call this as a filter bank and I have to do something to this filter bank to overcome aliasing errors introduced because of overlapping frequency responses. So, I think the message is very clear. So, non overlapping means steeper frequency transitions, frequency transition bandwidth slope is the transition there is a transition bandwidth, and if you look at the slope of the transition bandwidth it is steep, and here is more relaxed slope in the transition bandwidth region, which means it is easy to design filters, but aliasing is an issue. And in this case filter orders could be prohibitive, and no aliasing. Okay, here the filter orders could be prohibitive, but no aliasing. Here there is aliasing, but easy to design the filters. So, there is some compromise that we will have to do, but fortunately we have solutions. When we have to design digital filter banks, we can overcome these aliasing errors and have overlapping frequency response, but we design our synthesis filters somehow to cancel aliasing using our multi-rate operations. So, I think that is the whole idea in the design of these filter banks. Okay. And you may wonder why even should we take a signal and decompose this into analysis and synthesis filter banks. That means we have a signal, we have an analysis bank, and let us say we have these subband signals, and we take these subband signals, pass them through a synthesis bank, and we get back our reconstructed signal, say some x hat of n, this is some x of n, right. At this step, which is very important, there is a transmission that is happening over a communication channel. When we say we are transmitting over a communication channel, this means that we are playing with the bandwidth of the channel in some sense, right. And if we have stringent constraints on the bandwidth of the channel, then we may have to possibly compress the signal, right. Now, we have different frequency components that get filtered as we go through this analysis bank. I mean, this could be essentially a low pass version, and all of these could be band pass, BP1 dot dot dot, some band pass say N, and this could be our high pass, right. And depending upon the information content in each of the bands, I may have to choose my bit rate in such a way that I can throw away certain samples in each of the bands. That means I can adjust my sampling rate in the subband signals and basically quantize and do anything that I want to do to compress. And again I restore this sampling rate in the process of my upsampling, then I just get a set of signals here at the input of the synthesis bank, and then I try to reconstruct the signal. So, the journey here is under what conditions can I do perfect reconstruction. So, if I do not do quantization and I do downsampling here at the output of the analysis bank followed by upsampling, can I reconstruct perfectly? What are the conditions for filtering or choosing, how do I choose my analysis filters and synthesis filters to overcome errors due to aliasing, due to errors in phase distortion, possibly magnitude distortion in the frequency response, etc., etc., right. So, these are all various questions one would get, but I think you have to appreciate here that this is practical because when one thinks about sending these subband signals over a communication channel, then we will have to basically work within the limitations of the channel, and that is the real challenge here, how to design these filter banks. Okay. So, with this we will stop here. We will look into the discrete Fourier transform or the DFT as a filter bank. We will consider the DFT as a case study, and then we will generalize this towards other filter banks. Okay, we stop here.